Okay, folks, welcome to the Math Club today. Without further ado, let me introduce Dr. Alex Bay, who's going to talk to us about how to make a great design.
Okay, how to make a great design. My talks have consist of 4 parts. What is the design? What is a great design? And how to make a great design? And then it will be the closing remarks. Let's start. What is a design? Let's start with the game Spotted. This is just a game. It's called Spotted, and then these are how the cards look like. There are several ways to play with these cards. One of them look like this. So there is a pile of cards in the middle, and then each player will get a card. At the beginning, nobody knows what is the card in the middle, so it should be flipped over. And then once it turns over, every player have to figure out the matching figure on your card and the one in the middle. So for example, if you are pair 1, then you will check whether you have any figure that is in common with the middle one. Can you find the symbol? It should be the zebra. And then next one, if you're pair 2, what should you call? Balloon, yes, the balloon. And then pair 3, we call balloon as well. And then pair 4, what should pair 4 call?
Exclamation mark.
Exclamation mark. Yes, that is the yellow exclamation mark. Okay, now this is how to play with the game. Everyone has to find a symbol. It does take time sometimes, right? If you're having your pizza, you may not be able to find it. So the goal is to be the fast one, be the first one to shout the common symbol. Now, this game have different versions. Some of them is spot one, so you spot the sport equipment. You may also spot the common animals. You may also spot some common figures. And now I would like to make a spotted that is for crimson. Okay, and now I make my card. I have 5 cards, and I put each card I have 3 symbols. I like pizza, just as you do. So I put pizza in all my cards, and then I also put tiger there. So I have capital letter, uppercase letter, and the lowercase letter. Well, just because of the pizza, I'm sure that all the cards have one symbol in common, and everybody will call pizza. Okay, but that is not that fun because everybody just called pizza, not even anyone called tiger. So I will add another 2 cards. These 2 cards will have 5 symbols, all the uppercase letter. Another one card will be the lowercase letters. If I add these 2 cards, will the game still work? Why? Why?
If your bottom 2 cards don't have any symbols in common.
Okay, yeah, I'm sorry. We have to get a common symbol among any pairs of cards. So here we don't get a common symbol. So let me just get either infinity. Okay, so now I add a symbol infinity to both cards. It works. Okay, now then, I only get 7 cards right now. I may need more, otherwise it won't be fun. Any idea how to make the next one? But you have to be creative. If I have to make another card, I have to put something there. What should I put? Each one gives me a symbol. It can be a new one, it can be an old symbol. I need a card. You know, I have to make some money by making the Clemson sporty card. Okay, give me a symbol.
Put the infinity back on there.
Okay, infinity. Okay, your turn.
A T.
T. Do you like to get a new symbol on my card? Just get a symbol there. What do you suggest?
Right, then the pizza doesn't count.
Yeah, you can add pizza again. Okay, I will add a pizza. What do you want to add? A new symbol or an old symbol? I have infinity T, infinity T, and pizza. Okay, so that's what you have. Infinity T, pizza. Do I have to add more?
L.
L? Okay, that will be a good choice. L. Is it a good card? No. Hey, that is what you make. How come you say that is not a good card?
Yeah, two symbols in common with some of the other.
Yeah, well, you get two symbols in common that T and infinity here and T and infinity there. So if this is the middle card and you are the player who owns this card, then you will get an advantage. You will be able to spot it quickly. Now, well, it takes such an effort to make one card, but we have to make a lot of cards in order to have the game. And every time when we add a card, we have to think carefully whether that card have a common figure with all the previous cards. So it's not just, well, it requires some work and you have to check carefully. And of course, when you get more cards, you will have more difficulty in adding a new card. Now, we can turn this game into a mathematical model, and that will make our life a little bit easier. The way to do so is to to interpret a figure to be a point. So say here, I have 12 figures, and they just represented at points here, and then I have different cards. All these cards will appear as a block, well, actually just a straight line. And then if a figure is in a card, I would just say that a point is incident with a block. So the 5 pieces of card, they correspond to these 5 blocks here. And then these 2 tiger, well, all the letter cards will correspond to these 2 blocks. That is how I interpret it. And then if you do so, then if you need to add a additional card that will become figure with each of the existing cards, then it will just mean that I have to get a additional block that have a common point with all the existing blocks. So it's just like, okay, well, I can draw a line. Yeah. I have to figure out that it get a common point with all the blocks. So I may get some point here, extra point, and I can call them 1, 2, 3. That can form my new card. So that will be T, I, 1, 2, 3. And you have add 1 here, 2 there, 3. Oh no, I mix it up. You have add 1, 2, and 3 there, right? So by just working on this figure and then some blocks and some intersections, I will know how to find the point. Okay, yeah, that's here. Every time I just add a block in the figure, and then I check, okay, well, whether this block have any common intersection with all the existing blocks. If we have common points, then it works. It will be a class network. So that is a way to turn the game into figure. And actually, the mathematician get a name for what we have made. We say that a block design is a set together with a family or subset that called blocks. And all the elements of that set we call it forms. So in the design that I have made, I have all those pawns that contains all those letters, the pizza symbol and the infinity symbol. And then I get some blocks. You can write it as a subset of the pawn set. So you get all those pizza blocks, pizza cards, and then the uppercase cards and the lowercase cards. And of course, we have a way to visualize it. Okay, next we think about, okay, so now we know what is a design. Next we think about what is a great design. We have already covered quite a few of features when we in our discussion. Here are some features that will be preferred or actually necessary. Some of them are necessary in order to make such a game. For example, okay, each card contains the same number of figures. Now, if you get a card set with more figures, it will take longer time to find a common one. So it should be a preferred features. Okay, another one. Each figures appear the same amount of time in each card. Like if you get the pizza all the time, then I don't have to worry about much. I just prepare to shout pizza. So we may require that each figure to appear the same amount of time. Well, the next one is actually necessary because that is how to play the game. For any two cards, there is at least one common figure. And some of you have already mentioned or feel that there should be another rule there. It is for any two cards, there is at most one common figure. So you can't get two figures, and that will make the game unfair. And of course, we have to get more cards and more figures. This is just too small this time. Okay, now so the game started. Give us some suggestion how to define a great design. But okay, so let me just put all those properties into our design notation. So I just use our analogies again, change cards to broad figures to pawns, and now I get our properties. I want our design to have these three properties, or four properties. Each block has the same amount of pawns, each pawn is on the same amount of blocks. If you give me any two blocks, there will be one and exactly one common pawn. Now, I would like to say that such a design is great if all these four properties hold. But probably you may argue, well, this is just a game, and well, yes, this is some nice feature, but it just suggested by a game. Are they really so great? So instead of just use the spotted to say that okay, those features will make a great design, I will give you another point of view to convince you the property that I have listed will give you a great design. This is a statistic point of view. Okay, let's consider a scenario like this. You can also think about the math club talk. Maybe there are about 10 talks per semester, and then there are 15 regular participants. And now each participant attends on average 4 talks. Do you attend 4 talks this semester? Okay, well, then my number are not so great. not close to reality. Okay. Now we can have a very simple calculation. The total number of attendants should be the product of them, so that's 60, and then I can also calculate on average how many participants on each talk. And now each participant can give a score to each of the talks that they attend. So from 1 to 9, 1 is poor, 9 is excellent. Here maybe the score sheets that you can have. Some students may attend all the talk and give 9 marks for all the talk. Some students may attend most of the talk and use just rank them. So the range of mark will be quite diverse. Some students may only attend 1 talk, and you get a score sheet like this. Now, I would like to know how to design the best talk. Out of all these 10 talk here, which one is the best? Based on this score sheet. Oh. Which one should be the best? You know, some talk have more audience, but probably the score is not that high. Some talk have less audience. This one only get 1 audience, but his score line highest. So talk number 7, the average score for number talk 7 should be the highest, but probably you won't choose his talk. So we can't force any participant to attend a talk, so we end up with a score sheet like this. Statisticians have a method to deal with this. There is a model. The model is not that difficult. It's just say, okay, well, they can predict the score of the I talk given by the J participant, even that participant didn't attend the talk. The score will be given by general mean with the effect of the I talk. So if the I talk is better, then it will add a component for that, and then there is an effect from the J participants, and then there is some random error. Well, this is a statistic model. When will the model work best? Well, it works as I say, I think they use it all the time in all the scenarios, but sometimes we know that it will get a better estimation. And if you ask them, if you ask some statistician, they will tell you, oh yeah, if you can choose which participant to attend which talk, we will wish to check whether the design that they come up with the efficient patterns, variance patterns. They have a lot of concern when they make the model, or just to estimate how efficient the model would be. In our case, we get only 10 to 50 participants, 60 total attendance, then the talk will work the best when every participant attend exactly 4 talks. So instead of on average 4 talks, every participant attend exactly 4 talks. Instead of on average there are 6 participants on each talk, they will prefer to have exactly 6 participants in each talk. And if they can get more, they will surely ask for it. Like, okay, for any 2 talks, there are exactly the same amount of participants in common. So in that case, if you wish to compare 2 talks, you have 2 scores for you to get a reference. Okay, now okay, and if you remember what we have before about the design or the features of the grades design, then you may think of, well, actually I can also turn all these into the design 3D language. So that means calling each participant to be a block, each talk to be a port, then all the features here would become each block contain exactly 4 ports. For each port, there are exactly 6 blocks. For any 2 ports, there are exactly 2 ports. Now, this property is just the same as what we have when we talk about the game spotting. And that's why I would like to, well, actually many mathematicians do that. They say that a design is balanced if the following property holds. first one is each blocks have the same amount of pawns. And just because this talk is about grade design, so I would like to just to write down the definition. Each blocks have the same amount of the same number of pawns. Same number of pawns. That is the first criteria. The second one is each pawn is on same number of blocks. Same number of blocks. And the next one is for any two pawns. There are exactly the same amount of common blocks. Yeah, exactly. Same number of common blocks. Okay, so this grade design should be great in a statistical sense and also in a sense when you make your game spotted. Yeah, you can also check here. These are all the requirements that you want. Okay, so now we know what is a grade design, and it turns to part 3, how to make a grade design. Here I give you a very simple trick. This simple trick. Okay, I'm going to start with a design with 7 points, and I just name them 0 to 6, and then export the block. It will look like this. The first one is 0, 1, 2. I can visualize it in this way. So I get the 7 points, I put it in a circle like this. The first block is 0, 1, 2. Okay, so it will look like this. The second one is 1, 2, 3. 1, 2, 3. And then the next one is 2, 3, 4. This one, 3, 4, 5. 4, 5, 6. 5, 6, 0, and 6, 0, 1. So actually, if you look carefully, you find that well, there is not a big deal. It's just some consecutive number. You just add 1 for each block. So from 0, 1, 2, you get 1, 2, 3. And then when you add up to 6, you just turn it to 0 because when the figure rotates, then you get 6 back to 0. Okay, well, this is not a big deal. And I can do the same for the 7 points. And now I change a little bit. The block, instead of starting with 0, 1, 2, I start with 0, 1, 3. And I actually just do exactly the same thing. So the block, when I define it, it will be from 0 to 6. So say again, if you meet 0, if you see 6, then next one will be 0. If you see 6, the next one will be 0, and then you come back. Geometrically, you will just edit the block, keep rotating it, and then you get this figure. Okay, now, which one is better? The left one or the right one? Right one. Why?
Because on the left, they have the same number of points in common between all of them.
Can you hear his answer? I'm surprised that you guys can spot it. Okay, yeah, we can compare these two designs and try to check what features I have. Well, there are 3 points on each box. That is how I create the blocks for both sides. And then there are 3 blocks through each point. That should be true again. Well, because like 0 will appear in the first digit once, and then the second one, a second here, and then the third time will be here. So both of them will be the same. But if you ask, okay, if you give me 2 points, and now I check whether there is exactly 1 box pull them, then only the block on the right hand side will work. So well, some of you may already find out, but let me just check it. So you can pick any two blocks that you like, and then think about. If you take any two points, oh well, maybe we take 0. And then you look at all those blocks that passing through 0. So we get the pink one, we get the red one, we get the blue one. From that, you will find that, okay, well, 0 will be connected to all other points. But if you look at the design on the left, you get this block passing through 0, this one passing through 0, and then another one through 0. So there is no block passing through both 0 and 3 on the left-hand side. But for the right-hand side, it works. If you look at the destination here, it means that we get a balanced design on the right, but not a balanced design on the left. But actually, you can have a bit more. That is, on the right-hand side, any two blocks will have exactly one common point. This one is not that easy to see, but you can try. Like you just pick two blocks, any two blocks. Like here, okay, then the common one will be 3. And then if you take another one, the common one will be 4. 4 here. You can pick whatever you like. You don't have to tell me which two you choose. Just pick 2 of them and then check whether there is one and only one common point. Now, on another side, you can also do so, and I don't think it worked. I can give you 2 blocks that are disjoint. So like here, okay, they don't have any common points. So this side, the design in the left-hand side is not as good as the right one. Well, then it comes to another problem. How come 0, 1, 3 is better than 0, 1, 2? Well, let me just have a record. So if we start with 7 points, rotating 0, 1, 2 will not get you any balanced design, but rotating 0, 1, 3 will work. That will give you this one. You may keep on trying to see whether there are other blocks that help you to do that. So say 0, 1, 4, it doesn't work. 0, 1, 5, it works. It works and give you the same design. It's just because if you relabel the point using the green label, so instead of clockwise labeling the point, I now anti-clockwise labeling the point, and then I consider the pink block, that is this one, using the green labels. This will be 0, 1, 5. So if you're rotating 0, 1, 5, yes, that will give you a balanced design, but it is just the same as what you can have from 0, 1, 3. And you can keep on to do that. 0, 1, 6, it won't work. 0, 2, 3. 0, 2, 3 will work, but 0, 2, 3 is actually just this block. When you look at the green labels again, 0, 2, 3, the full one. And then you can keep on to check. After you exhaust all the triple, you may try to look at some full subset of these 7 points, and then you keep on exhausting and then see, oh, which one will give you the balance. And it turns out that only 0, 1, 3 and its relative will give you balance design. So by relative, I just mean that we can relabel it or what. So this 0, 1, 3 is very special, right? Or let me call it a magic block. So for 7 vertices or 7 points, the magic block is 0, 1, 3. Okay, the next case that you can find a magic block is when you have 13 points and the magic block is 0, 1, 3, 9. Now, what does it mean? If you take it that apart, so you can consider like for 4 A's are the same, then you will get 13 points, and then you start with the block 0, 1, 3, 9. Well, let's consider 0 as king, and then 1 is 8, 3 is 3, and 9 is 9, and you get the first block, and then you just add 1 for each of these cards, so that means 8 becomes 2, 3 becomes 4, 9, 10, and then king becomes 8, and then of course you can do it, and then at the end you will exhaust all the cards, and now you get 13 blocks. I say that this is a magic block. It will mean that it gives you all the nice features that will include there are 4 points on each block. That is not so exciting. We know that already. Every 4 points for each point there are 4 blocks. That is again not so exciting because I know that I get 4 A's. So I get 4 twos, I get 4 threes, and of course each point will appear on 4 blocks. What's more is for any 2 points, there will be exactly 1 block. So this one again, you have to just check carefully. Like you can give me 2 numbers from A to K. Anyone here pair? Just give me a pair.
Jack and 3.
Jack and 3. Let's see where is Jack and 3. Oh, this one. Any other 5?
7 and 8.
7 and 8. Oh.
Second row, third column.
Oh yeah, I see it. Okay. And I can guarantee you there is one and only 1 block containing any 2 points that you have. And now we also get another one. That is, if you give me any 2 blocks, there will be exactly 1 point in common. So like if you take these 2, the common one will be 3. If you take these 2, the common one will be 8. And you can do whatever you like. Just pick any 2 blocks. You should find exactly 1 point in common. So this is a gift that I hope all of you will like it. I often play this game with some kids, and then they will feel very amazing that how come you can do this trick. Okay, now, okay, we get a magic block for 30 points, and if we move on, for 21 points, you can also have a magic block. 31 points, you also get one. This is the 21 points version. This is the 31 one. Let's have a guess. What is the next one? If I have to increase the number of points, what will be the number of points for the next magic design?
43.
43, well, good try. How can you get that?
Just observe the difference between the 2 adjacent points, and 6, 8, 10. So next should be 12.
Wow, that's a very good try. One way to check it, well, your way work, and your way work. This way will also work. This number, we can just, well, it's just addition, but somehow it has a pattern. So we may think that the next one is 6 squared plus 6 plus 1. Squared plus 6 plus 1 is 43. Unfortunately, there is no magic block for 33. You know for that, you think there will be. You know, that is not. Okay, well, the case for 7, it worked. Actually, it is the game spotted. That means it gets 57 symbols. Each card have 8 symbols, and 8 is rotated. So, well, you may keep on asking, okay, well, 8, does it work? 9, does it work? And then, well, 10, oh, that doesn't work. It is?
Composites. Is it composites with different primes?
You guys are so careful. Okay, okay, 10 doesn't work, 11 work, 12 works, and of course you will ask, "Hey, how come some numbers work, some numbers doesn't work?" And some of you have already found out the answer. It works if it is a power of a prime. So like prime is a 2, 3, 5, 7, 11, and then you get 4, 8, 9 to be prime power, but 6, 10, 12, they are not prime power. Okay, then the next question would be, well, if I give you a power of prime, how to find a magic block? So you seem to predict that if I start with a prime power, you will be able to get the magic block. How can you find that? The answer is from the finite theory. Have anyone studied finite field? Okay. So if you haven't studied it, that will be good. It just motivates you to study well in abstract algebra, and then one day we can study finite field, and that will tell you how to get the magic block for the great design. Okay. Now, so we know how to find the magic block. Here comes to the end. My cosine remark is a conjecture. It is called prime power conjecture. It says that if you get a design with this number of bonds, so that is what we have for the magic blocks. Each box contains n plus 1 bond. Each bond is on n plus 1 block, and then the last one is any two blocks. Oh, any two blocks. Let's see. Any two balls intersect at exactly 1 point. Sorry, I missed the word there. Then n is a power of the prime. That is a conjecture. This conjecture is a pretty, I should say, pretty famous one in combinatorics. If you can solve it, I will be very happy with the paper with you. Okay, now this conjecture, we already get a little bit taste of that. If it is a prime power, we can use finite field to get such a design. And even if you don't use field theory, there is also some other way for you to get a design with all these properties. However, for people just no matter you use the magic block or not, so far, all the design that people have found so far with this n that is power of the prime, and the smallest open case is 12. So that is quite a small one. Well, of course, people try to use computer to solve it, but you can think about that. That involves quite a lot of combinations. And this prime power conjecture is called prime power conjecture for projective plane. It's because this kind of design, we call it a projective plane. The reason is if you change block, replace block by lines, then here I just require any two lines intersect in exactly 1 point. Now, most of the time, or just in the world that we are living, we have parallel lines. They are parallel lines, so they don't intersect. But in the projective space, two lines will intersect. And if you somehow know how to get a projective plane, you will find that in the finite case, any projective plane will have this property. And that's why this is the prime power conjecture for projective plane. And if you feel interested in that, I will encourage you to study geometry. Yes, to study geometry and of course algebra as well. Another closing remark is reference. This is a quite introductory book. I also find another one on design theory. If you like to know more, you can look up for keywords. Design is the official name. The standard name, The balance is the word that I say great design, and then normally they call it balance incomplete block design. So that is BIBD in short. And then I have mentioned experimental design that using statistics and also projected plane. The magic block that I have mentioned is called different steps. And then, yeah, that is the kind of conjecture that I've mentioned. If you just come because you wish to know how to make some good figure, you may find this website interesting. It has some demonstration on how to create some projected planes of low order. So like this one, this is order 7. Just you don't have to, you just have to click a few buttons and the software will generate a very nice design for you. And I am also interested in having some course in the coming academic year on creative inquiry course or independent study course. So if you are interested in what I have mentioned in this talk, let me know. I may also give another talk in a math club next semester, more on geometry. If you are interested in geometry and wish to work with me for a creative inquiry course or independent study course, please also contact me. And thanks for coming.
Question. Well, I have a question. Can you go back to the previous slide? Just so I got it right. The last bullet point, any two blocks, exactly 1 point.
Yeah,
What do
any
you,
any two block will intersect in exactly 1 point.
okay. Yeah. See, I'm gonna go home and solve this tonight. Yeah, that ain't happening. So, yeah, I was gonna ask another, like, what was known about these kind of finite geometries, but I think the fact that it's open with n equals 12, even for this problem, shows that this gets very complicated. Any other questions? All right. Oh, I'm sorry, go ahead.
Do you study these designs from like a more statistical aspect too, or just more about like there's some of the statistical properties, or you just study like the algebraic properties of combinatorics side of this?
You mean,
Yeah.
I will be more interested in the
Oh, okay.
theory.
I see.
Other questions? All right, let's take our seat. Thank you. Okay, thanks for y'all out there showing up, and we will see you next week. We've actually got an undergraduate speaking on some very interesting stuff. He's actually going to talk, I believe, about the n-body problem, which, how many of you know what the n-body problem is? So this is a rotational, yeah.
Orbits and
Yes,
space.
that's right. The two-body problem is well known. It's stable, right? Well, like my wife living in Atlanta, that's not what I mean. But two orbiting objects, stable. But even a three-body problem is not completely known. And it can be unstable. Like if you have three orbiting objects, in theory, it's possible for two of them to gang up on the other and throw it out. The n-body problem is very complicated, so it should be an interesting topic. So y'all have a good weekend. It's dark out there now. And we'll see you on Monday.